All right. So welcome to this week's non-commutative geometry and topology seminar. This week we have Robert Neagu from Leuven, who's going to tell us about admissible KMS bundles on classifiable C-star algebras.
Thank you for the introduction and for inviting me here. Greatly enjoyed it so far. So the goal would be to try and pick up from where Aaron stopped and kind of try to demystify this a bit and see, okay, what are the possible KMS states that we can have, or what is the structure on these things, or what do they tell us, right? So if we know them, like, what can we do with the action? Okay, does this tell us anything about the action or not? Okay, right. So I'm gonna try to make clear what do I mean by these bundles and classifiable and all of this, but as an intro, like really as Aaron motivated, this comes from physics, and in operator algebras they picked up like in the 70s through the work of Kohn. So maybe you've heard this Tomita-Takesaki theory. So really what happens there in the von Neumann algebra case is very canonical. So there, if you have a von Neumann algebra and any faithful normal state on your von Neumann algebra, there exists a canonical flow, so canonical action that you can build from that state. And that state will be a KMS state with respect to that canonical flow, okay? So everything is very canonical, and this is precisely what Kohn used to classify some of these type 3 factors, if there's anything, right? Because there you have a state, and then with this canonical flow, you can decompose your type 3 factor as some type 2. But if this doesn't say anything, doesn't tell you anything, don't worry, I'm not going to talk about factors, okay? But the idea is that in the von Neumann case, this is very canonical. In the C-star case, though, there is no, or at least so far, there is no canonical flow, okay? So if I give you a state on the C-star algebra, a nice state, I don't know if there is a flow, like such a continuous action of R, for which this state is a KMS state, okay? So it's a bit unclear what's going on. Okay, so the goal would be to understand the set of all KMS states for a flow. Okay, so let's say in this talk, A will be separable, and will be a separable unital C-star algebra, and yeah, let's say alpha will be such a continuous action of R on A, okay, by isomorphism. And the goal is to understand what are the possible KMS states here, okay? So for this, we can introduce some notation. So we have such a pair, S alpha, pi alpha, which I want to think as the set of all KMS states for alpha, okay? So this you can think, for example, you can see this as pairs, omega beta, which are omega is a state and beta is a real number, such that omega is a beta KMS for alpha A, okay? And what is this pi? This is really like, for any KMS state that I have this temperature, right? So actually, this pi alpha, if you want, maybe I just put alpha. It's alpha, but this pi alpha is just the projection onto the R coordinate. Okay, so given a KMS state, I give you the temperature of that state. That's exactly what it does. And in fact, this is continuous. Okay, and then you might ask, okay, what is the topology that you want here? Well, it's the weak star topology on the state space, so you just take like the subspace here. Well, all right. So the goal is to understand this pair. So this is continuous. Okay. So does this have any structure? Okay, like what can it be? Okay. So Aaron gave us this example of the gauge action on the Kunz algebra, where this just consists of one point, okay? A unique beta and a unique KMS at that point, okay? But maybe maybe at a given beta you have more KMS states. Maybe you have none. Maybe, right? These are the kind of questions. Well, what is this? And I'm going to try to generalize a bit this example of the gauge action. To make it again on O2. So let's say if A is O2, and let's say I pick some numbers, L1 and L2, some real numbers. Well, I can define a continuous action of R in a similar way, right? So I need to see what I do to the generators. So S1, I send it to E to the IT, L1, S1, and alpha T of S2, E to the IT, L2, S2. Okay, so this is for any T. Okay, so in Aaron's example, L1 and L2 were both equal to 1. Okay, but in principle, I can vary them. So what happens here? Let's say they are non-zero because I don't want to think of like trivial cases here. So there are two possibilities. Well, quite uncountably many, but let's say two possibilities of interest. So the first one is if L1 and L2 have different signs. Okay, so the product is negative. They have different signs. Then alpha has no KMS state. And the second is if they do have the same sign, then alpha has a unique KMS at beta given by the equation e to the minus beta L1 plus e to the minus beta L2 equals 1. So this is exactly what Aaron did, but you just put an L1 and L2 in there. It's the same calculation. If you have such a KMS state, when you do the calculation that Aaron did, you arrive at this equation. You need this to hold. Okay? It's the same calculation. And now you can look at this and say, oh, if L1 and L2 have different signs, then this can't work, right? Because one of these guys will be positive and e to that will be bigger than 1, okay? So you have no KMS state. If they have the same sign, then this is possible. You'll find the beta such that this equation holds, okay? And then again, it's unclear, okay, this doesn't show the existence of a KMS state, but it tells you that if it exists, that's the temperature. And in fact, like what happens is exactly like in Aaron's example, the KMS state, it's pretty explicit actually. So if you want some intuition for what it is, well, what you do is you take O2, and there is a canonical conditional expectation onto the car algebra, M to infinity. Then you'll be corner this is like a car algebra, okay? But what happens is this is the fixed point algebra of O2 under the gauge action. Okay, so you put gauge action. Okay, and now what you do, you compose with a state on the car algebra. That's not, you don't want the trace on it, but you want the trace somehow scaled by a matrix with this beta. Okay, so not necessarily too important what it is, but this is how the KMS state will look like. Okay, so it factors for this car algebra. Okay. Now, so in this example, you already see two things, right? I mean, if I change these parameters, I can get no KMS state for this flow, right? But if they have the same sign, that I get 1 at the unique beta. Okay, generalizing exactly what happened for the gauge action. Okay. So now from here, I want to ask, okay, but what is this set, like S alpha pi alpha? Does it have any structure? And maybe I put it here, the proposition, which this is, I would say, is probably folklore. goes back to like work of Elliott, Brotelli, and Kishimoto. I found this formalism by Klaus Thomson. So in this scenario, if A is a unital separable sister algebra, as we fixed, and alpha is such an action. Okay, so usually I call this flow, but you probably figure this out because I said it. So if this is the case, then the set of KMS states, so this S alpha, I think of it as a pair with this continuous function that's in there. This is what's called the proper simplex bundle. Okay. So now if you think that you don't know what a proper simplex bundle is, that's exactly the right thing to think, because you shouldn't know what this is, because this is not like a well-known thing. Okay, it's sort of like an ad hoc terminology. But let's see what this is. Okay, so what is this terminology? So definition is, in general, a pair S pi is a proper simplex bundle if you have a bunch of conditions. So S is a locally compact Hausdorff space, second countable if you want. So pretty much anything you can think about, which is nice. So second countable, locally compact Hausdorff. So S should be like the set of KMS state, right? So this pi is the function that tells you the temperature, okay? So this pi is continuous. And now we have more structure. So if you look at the inverse image of any singleton, so for any inverse temperature T, now you take the pre-image of this. What is this? This is like the set of T KMS state, or beta, if you want, right? This should always be a Choquet simplex. It is a compact metrizable Choquet simplex. This is for any T in R. Okay. Yeah. It's unclear to me, to be honest. Maybe, yes. No, it's the set of KMS states, the S. Yes. Yeah, the temperature. Yeah. So I guess if you want this to be well defined, yeah, it should be unique. Yeah. But yeah, okay. I guess what I mean, okay, if you take a different flow, sure, you can have that state to be a KMS state of a different temperature to respect to a different flow. But okay, if you fix the flow, then it is well defined. That's a good point. Okay, so what do I mean by this Choquet simplex? I mean, I don't want to give like the formal definition of this. So what you can think about that is some kind of infinite dimensional generalization of like an n simplex. Like an n-dimensional simplex is just like, what it is. So a two-dimensional one is the triangle, three-dimensional tetrahedron, and so on, right? So this is some kind of infinite dimensional generalization of this, where any point, essentially, you can find a measure such that X is the barycenter. But like to go on what Aaron was hinting at, remember that zero KMS states are just traces. Okay. So really, on a unital sister algebra, the set of traces is always such a compact metrizable Choquet. Okay, so this somehow tells you that at any temperature, the set of beta KMS state is like a trace simplex. Okay. Right. So then S is really, you can think of it as some kind of like disjoint union, like a continuous disjoint union of like these Choquet simplexes, right? At each temperature, you have such a Choquet simplex, and you're trying to glue them together, like in a continuous way, okay? Here, we haven't really seen it because at a unique KMS at a unique beta is not really much continuity going on, but you can have a lot of nasty things, okay? And well, unfortunately, I'm not done with the definition of this. So there are a few extra, let's say, nice behavior properties. One is that this pi map is proper. So the preimage of a compact set is compact. So it is compact for any k compact. And the other one is somehow that you can separate points. So as in the case of like traces, if you want, you can consider like affine functions on this first space, and you will separate points with them. So this is it's not so easy to define formally, but you can define essentially like some continuous functions on this set. So I'm denoting it by A as pi. So this is just some continuous function. So this is just something in C of S, such that on each fiber you're affine. Okay. So remember, on each fiber, which is like these preimages of beta, you're actually a Choquet simplex. So you want to preserve this affine structure, right? So on each pi inverse of T, this F is affine for any T in R. Right, so some kind of nice convexity preserving function, and the separation. So this is just a definition. So now the point is that for any two distinct points in S, you can find the function f in here such that f of x is different than y. Okay. Again, this property holds like for Choquet simplexes. So if you have like such a Choquet simplex and you consider affine functions on it, you can always separate points by this affine function. So this just tells you that what happens like fiber-wise, actually you can ensure that it happens globally. Okay. So yeah, I think the message is that this is like a complicated structure, and you might want to think of it as a continuous union of this Choquet simplicity. Okay. Right. So then the question one can ask is like, okay, if I know that alpha is such a flow, I know that the set of KMS states is such a proper simplex bundle. But what about the converse? Okay, so the converse is like if I give you like such an S pi, a proper simplex bundle, and a C-star algebra, can you build a flow alpha such that S alpha pi alpha is the same as S pi? Okay. And for this, I need to tell you what do you mean that these things are the same? Okay. So there is like a notion of isomorphism that one can define. If I write here. Yeah. Okay. So in this category, if you want, there is a notion of isomorphism. So let's say S1 or S pi is isomorphic to S prime pi prime if there exists the homeomorphism from S to S prime, homeomorphism. And now you can think, well, I want to preserve the structure. So what would I possibly want? Well, I want to send beta KMS states to beta KMS states, right? So how do you translate this? You just say that pi prime composite phi is pi. This is one. Also, this S and S prime are not just like any locally compact Hausdorff spaces, but they have some kind of affine structure fiber-wise. So you want to preserve that affine structure fiber-wise. So phi is affine on each fiber on pi inverse of t for any t. Okay. Yes, exactly. So now I can ask the question of like, well, given S pi proper simplex bundles, I just abbreviated by PSP because it's a bit mouthful, and A, if you want the unital separable sister algebra. Can you find alpha? Can you find alpha flow on A such that S alpha phi alpha is isomorphic to S phi? Okay. So is this question clear? So again, I really want to think of this bundle as giving me some information about the action. Okay. So I fix the sister algebra, but I can vary potentially the action. And the question I'm really interested in is like, if I give you two actions, when are they the same? That's what's lurking around, right? And this proper simplex bundle, this says alpha pi alpha, is what's called an invariant for my action. So for any reasonable notion of equivalence between actions, this notion would be something called cocycle conjugacy, which is something like, well, you find an automorphism of A that somehow like permutes the actions, but maybe not on the nose, but up to some unitary cocycle, okay? So let's say if alpha and another action, sigma, are equivalent in this sense, then these guys should be isomorphic, okay? But I'm gonna come back to that. So hence, because this is an invariant, I want to understand it, okay? So this is sort of an existence question, okay? How bad can this be? But to answer this in general, it's a bit too much wishful thinking, okay? Like if I just give you any unital separable sister algebra, yeah, this is it's a bit too much, okay? So we're gonna restrict and try to understand the other term in that title, which is classifiable, okay? So I'm gonna restrict on a nice class of sister algebra. And well, if you actually see the definition, you might not agree that it's nice. So that's why you won't see all the adjectives. But what's the class on that I want to restrict? So this is like a really big theorem with many people, which says that there is a nice class of sister algebras. So, well, depends what you mean by nice, but for me, it's like there is a class, let's say curly C, of simple sister algebras. Okay, so simple just means what you think it means, like you don't have non-trivial close two-sided ideals, which are classified up to isomorphism by an invariant consisting of K-theory traces. Okay, so what do I mean by this? I have this class C. I take two sister algebras in there, A and B. To them, I can associate some invariant. These are these K-theory traces. Well, traces just means I look at the set of traces on the sister algebras, and the K-theory, I look at the K-naught group and the K1, okay? But if you don't know what that is, it doesn't matter. It's an invariant, okay? And what I say, well, if the invariant of A is isomorphic to the invariant of B, in that category, if you want, then A is actually isomorphic to B. Okay, so that's kind of one part of the theorem, right? So A is isomorphic to B if and only if this invariant of A is isomorphic to the invariant of B. Okay? But actually more is true. And this is crucial usually in applications. This invariant is again something that can be defined abstractly, like we did here with this proper simplex function. And actually the second part of the theorem tells you that for any nice compatible invariant, there is a C-star algebra in my class C which realizes that. Okay? So for any inf, there exists A in C such that the invariant of A is this inf. Okay? So if I'm looking for an orange chair, that's it. I can realize it. Okay, that's kind of the idea. And more is true actually. This class you can not only classify algebras, but you can classify maps between them. So if I give you like a map between A and B, where A and B are in C, if I give you actually two maps, I can tell you when they are the same. Okay, so you can actually classify if you want automorphisms of A in C. Okay. Up to some notion of equivalence, which here will be up to approximate unitary equivalence. Okay, so some weakening of unitary equivalence, but yeah, let's say up to approximate unitary equivalence. Okay, and this would mean what you think it means. Like if you have two maps, then I don't find a unitary such that which conjugates one map into the other, but I find a sequence of unitaries such that the difference converges to zero in pointwise in norm. Okay. Right. So now I want to restrict to this class. Maybe yeah. Maybe I move on this side because I'm not sure you can see that. Can you see if I write in here? Yeah, but hopefully. Okay. Well, I'm just gonna, yeah. Okay. So for this class, now I can ask the question, and the answer is yes. So let's see. This is a theorem, and this is due actually again to many people. In let's say in special cases, so it really it goes back. Let's say Thomson proved this in the case when A is some AF algebra. Then Elliott, Sato, Thomson essentially generalized this to cover a larger class, but which is not the whole C. That's the point. Then I generalized it even more, and the final result will be in joint work with Johannes Christensen, or myself, and Gabor Szabo. Okay, and the statement is like this. So it's pretty much the answer of the theorem, but with some other bells and whistles. Okay, so let A be in this class C, and S phi be a compact simplex bundle such that the fiber at zero, so pi inverse of zero, is isomorphic to the trace space of A. Then there exists a 2-pi periodic flow, alpha on A, such that, well, you realize this S alpha pi alpha is isomorphic to S pi. And I should say, moreover, if A has no traces, S can be proper, actually, can be back to proper. Okay, so let's see what's going on here. So this is really like an answer to the question, but with some extra assumptions. So one of them is that I require S to be compact, just as a topological space. Okay. And I want the fiber at 0. So if I do the 0 KMS states actually to be all traces. Okay, so if you remember, we had this this comment about KMS states that they have to be invariant, right, under the action. So a priori, if you have KMS states at 0, they should be invariant traces. Okay, there is no reason why all traces are invariant. Okay, but this is a restriction if you want for this. So we can build a flow such that actually all traces are invariant. Okay, then you can find actually a 2π periodic flow which realizes that. But the comment is that if you have no traces to begin with, so your sister algebra has no traces, for example, these Kunz algebras that are undefined, then you don't need to assume compactness there. Okay, so there you don't need to assume compactness, and moreover, this is also redundant. Because if you have no traces on your sister algebra, you can't have invariant traces. So the inverse temp, like the fiber at 0 has to be the empty set as well. Okay, so these extra assumptions are only in the case when you have traces on your system. Yeah. Sorry? Hi. It's not surjective, no. It could be even the empty set if there are no invariant traces, but I think that's quite unlikely. If you have a unital sister algebra, I think actually you should have an invariant, an invariant trait, because you have an action of an amenable group on a compact state. I think it has to have a fixed point. Should have a fixed point. Yeah, I think that. But for sure, it might not be the whole thing. But, yeah. Okay, and also here, like this compactness really means that the set of temperatures is compact. Okay, so the set of possible temperatures for your KMS state is bounded. That's what it does. Okay. So this answers this question, and I want to tell you a bit like what is a strategy for proving such a thing, not with details, and like how this 2π periodic flow comes, like why is it 2π periodic? Okay. Yeah.
Sort of sanity check. If my bundle just is a single simplex above a point, let's say one is a single simplex above 0, and another one is a single simplex above 1. These are not isomorphic, are they?
They are not isomorphic, yeah, because the temperature is different, right?
Right.
The isomorphism has to send beta KMS to beta KMS.
Right.
Yeah, exactly.
Okay, gotcha.
But you could have that the state can be different, right? So if you have two different states at the same temperature, these bundles are indeed isomorphic.
Right.
Okay, so it doesn't have to be the same state.
Okay.
Thanks. Okay, so the strategy here is like this alpha comes a bit like from abstract nonsense. Okay, as you can probably imagine, because to build such a thing like from S, and it's like it's a bit of a non-go. Okay, so that's why I assume that this A is in C. So the steps to prove such a thing are something like this. So first, well, the big idea is that you want to realize A as a full corner of a cross product of this form by the integers. where B is again some C-star algebra and gamma is an automorphism of that C-star algebra. And you want to realize A as a corner of this, okay? So what I mean by this is really, I mean, it's isomorphic to some P, B cross Z, P, where P is actually a projection in B. Yeah, it's a projection. Okay, so this is the goal, and the second is at alpha is the dual action of gamma. So yeah, corner, sorry, corner. Yeah, so yeah, you cut down by projection. So what is this dual action? Whenever you have an action by an abelian group, in this case the integers, you can form the cross product, and in here you have a canonical action by the dual group of Z. It's like Pontryagin duality, right? So in here, what is the dual group of Z is the circle. So there is a canonical action of the circle on this cross product. And you can make sure that this action fixes this P, so it induces an action on this corner. Okay, so that's kind of the technicality there. And this dual action, so this dual action, I denote by gamma hat, this is this 2 pi periodic flow, right? Because any action of the circle, I can extend it to the real numbers, like by periodic. So far, I mean, there is no reason like why such a dual action would realize that simplex bundle, right? I mean, the whole point is that you have to encode the information of the simplex bundle into your choices of B and gamma. So you need to build them in such a way that the dual action actually does what you want. And here is where it's a bit of like abstract nonsense. This comes from classification. So, well, in between, to get this one, you really build invariants for B and gamma and use classification. So what do I mean by invariance? I mean exactly what I said here. For any such invariant, I can find you a sister algebra which realizes that, okay? So essentially what I do, I build some abelian groups coming from the invariant of A and this simplex bundle S. I build like a Choquet simplex, which is a trace space. And then by classification, there is a sister algebra B which realizes that. And now I build an automorphism of this invariant. And again, by classification, there is an automorphism of the algebra which realizes that. Okay, so the whole subtlety of the construction is in this choice of this building B and gamma, okay? And then there is this is one bit where I build this cross product, but then I have to check somehow that this A is isomorphic to this cross product, okay? So there I use the first part, right? Remember that A and B are isomorphic if and only if they have same invariant, right? So you check that A is isomorphic to this cross product, again, by checking the invariance by classification. All right. So this is try and give you a flavor of like what kind of things you can do with this, okay? But to actually how to do it, how to build these things, it's technical and perhaps not very enlightening, okay? But you can imagine that you need to use the information both from A and from S, okay, to put in the construction. That's the idea. Okay, but now we can ask, okay, like we answered the question like, given such a proper simplex bundle, we can always realize it, okay? So it's some kind of structure that we can hit all the time, okay? So now I want to understand, like, okay, how good of an invariant this is. Like, is this actually giving me a lot of information? It has to give me some information. So this is related to a previous question, which is like, if your actions are the same, are these invariants? Is this an invariant? And the answer is yes. Okay, so if alpha is, so well, let's say alpha and sigma are some flows on A, such that they're equivalent, such that alpha is equivalent to sigma, and really here I mean co-cycle conjugate. Okay, you can also think of an equivariant isomorphism from A to A. Okay, so that flips the action. That's good enough. Okay, so if that's the case, then these bundles S alpha pi alpha is isomorphic to S sigma pi sigma. Okay. Yeah.
So is it clear that this dual action leaves invariant the traces on?
The dual action leaves invariant the traces on the cross product, you mean?
I guess.
Yes. So it's like so this is like a really old result. So the invariant traces under the, well, you essentially build it like this. I think that's kind of the point. Under enough regularity, all the traces on this cross product should be coming from invariant traces on B.
Right. Yes. Yes. So I'm just wondering what. Okay. So this condition that the fiber 0 should be the full trace space. My question is whether this is clearly satisfied in this.
Oh no, it's by construction. Yeah.
Fine.
So
Okay.
Yeah.
Right.
So it's
Okay.
It's a check field based on the construction.
Okay.
Yeah.
Thanks.
Point. Yeah. Yeah. Okay. Right. Okay. So to see like maybe how good of an invariant this is, or like if this is some kind of information at all, we can take a baby simplex bundle. Okay. So we can go back here to our favorite example in O2. So here, I want to go in on the case where, yeah, perhaps even, let's say we have KMS state, because I would rather have them than not. So let's say your L1 and L2 have the same sign, and you have a KMS state of this beta. One thing that you can do, for example, is let's assume that L1 and L2 are rationally independent. So they are rational over Q as a vector space. And in particular, this would mean that this flow can be periodic if this L1 and L2 are rationally independent. Okay, you can't get periodicity there. Oh, so maybe on the other side. But then, if you apply this theorem to A being O2, so O2 is in this nice class C, then this theorem gives you a 2 pi periodic flow such that there's a unique KMS state, a unique beta. Okay? That flow can't be this one, right? Because like one flow that's like 2 pi periodic can't be the same as one which is not at all. Like there won't be any conjugacy between them like this, okay? So in general, there will be like further invariants needed. I mean, these ones you can distinguish, like as an aside comment, you can distinguish because whenever you have a KMS state, you can do the GNS representation on your sister algebra. And in this case, if if they are rationally independent, the GNS will give you a type 3-1 factor, while that will give you like a type 3 lambda factor. So these types are different and the actions will be the same. Okay, but this is just to say that there are potentially more invariants, and in general, yes, more invariants that there are needed. Okay, so I will end by like telling you, okay, like let's look at a class where hopefully this actually tells us something more. And this is exactly the class of those flows. So I want to denote by alpha Beagle the flow on O2 defined as in there, where L is, this pair L1, L2 is something in R squared. Right? So this gives me a family of flows on O2. Okay, so you can ask like, okay, when are they the same? Like just in this class, okay? Because, well, for example, like I can choose like so many pairs where they have different signs. In particular, no KMS states. Okay, the answer is yes, they have to be the same. So this is a theorem. So to make my life easier here, which this is needed, we need to assume to begin with that L1 and L2 are independent, are rationally independent. So let's assume this L1 and L2 are Q linearly independent. So if you want, like this is to ensure that you don't have periodicity, and it ensures some kind of simplicity. So in particular, the cross product that you form will be simple. And that's the idea. So the theorem is that if let's say L1 and L2 have different signs, so they are as above, but I also consider L1 prime and L2 prime, again, Q linearly independent with different signs, then alpha L is the same as alpha L prime. Okay, so this means this cocycle conjugacy between them. Okay, so here, like if you want, like the set of KMS states is some kind of like total invariant for this, okay? Of course, this is like a very specific example, but okay. This is not an easy theorem. So this is the thing about flows. Even if this is like the construction of this is quite elementary, to prove this, it's quite difficult. Okay, so this has been done like quite, let's say, bare hands by Kishimoto, and it's part of like a more conceptual, more general theorem of Szabo, which shows this for a bunch of flows. But really, the key property here. So here I'm gonna mention this is that these as alpha n and alpha L prime have the Rocklin property. So again, this is like a technical property that's commonly used in this business that you can ask me after. I will happily tell you what it is. But the idea is somehow that it poses like a bunch of like K-theoretic obstructions here. So in particular, things like you can build a bunch of cocycles. So if you think about cohomology, it forces a lot of cocycles to be co-boundaried. That's more or less what it does. So this is like a very strong property, okay? Which facilitates this classification in a way. That's the idea, okay? Right. But this was the situation where there are no KMS states. So this influence is due to Kishimoto, and more general theorem due to Szabo. So what about when they have the same sign, and you actually have a KMS state? So this is what I prove. So, well, this is more complicated. So if L1, well, so let's say the set of L1 the set L1, L2, or the set of pairs like this, which are Q linearly independent, and they have the same sign. So let's say they are both positive. L1 and L2 are positive. So for which this flow alpha L is classifiable, so this is not, probably it's true for all of them, but the best so far is that this forms a G delta, forms a dense G delta. G delta set, you want in 0 infinity. Okay, so let's briefly decipher this. Like, given two positive real numbers, L1 and L2, right? So they will be in here. Take them to be linearly independent, right? So you want the quotient to be an irrational number. So you can ask about them, what do I mean by this is classifiable? It means it falls into some classification theorem that can tell me like when things are the same or not. Well, this theorem tells you that almost all the time you will be in such a classification theorem. Okay, so for a dense G delta set of such pairs, your flow will have a nice property that you'll be able to say when is the same as others or not, based just on the temperature of the KMS state. Okay, so they will be classifiable by the beta there, by the temperature. Right, and maybe as a final comment, this will be like very different than this situation, because these flows like will be nowhere near this Rocklin property. So this Rocklin property, one thing that it does is like it tells you that there are no KMS states in general. So if you have KMS states, that's a big no-no. You can't be like that. But what happens here, and this is like a common idea that we saw there, we can always build a cross product, and then we have an action of the dual group on the cross product. What is the dual group of R? It's just R. So you have another flow on this cross product. What you can show is that that flow has the Rocklin property, but again, not all the time, but generically, okay? So for generically many things. And then you can classify that by other machinery, okay? So maybe I will stop here. Yeah, thanks for your attention.
Any questions?
Could you please explain more about the classifiability of alpha L? You say that somehow, but
What?
but the classifiability of alpha L.
So it's classifiable in the sense that like if I give you another flow on O2, which let's say satisfies the same, like let's say it's not periodic and it's nice, then it has to be the same as alpha L if and only if it has a unique KMS of the same beta. So the invariant will be the set of KMS states. Yes, which means there is just a point at one beta. So in particular, you can view this classifiable in this class, right? Let's say I give you two pairs, L1 and L2, and L1 prime and L2 prime. It is possible that they give the same beta by this equation, right? This pair is not at all unique. So this tells you that generically, when I pick two things at random, most of the time they will be equivalent if they have the same beta, right? That's, of course, like the goal would be to get rid of this dense G delta thing, okay? But yeah, this is quite difficult, and it's the best, let's say, so far. So, yeah.
Just to follow up on this dense G delta. I mean, so you know this work of Andrew Dean,
Yes.
right?
Yeah,
Is it just I mean, so he's talking about the cross products, and maybe just to further say, like in these two scenarios you have, in the first case when you take the cross product you get O2 tensor K,
yeah.
right? And then in the second case you get the stably projectionless thing.
Yeah.
And then Andrew Dean shows that there's a dense G delta set in the second case where you get something, a classifiable cross product essentially. Is that related? Your dense G delta and his dense
My
G
G
delta?
delta is like an intersection of that G delta and another G delta.
Right. Okay.
So yes, you need that. Essentially, I mean, you can do that, but what I show is that this alpha L will be generically equivariant is that stable, which shows the same thing.
Okay.
So then you will be in the W tensor K situation, but then you need something about the action to be able. So there's a classification of Gabor on Rocklin flows on this stably projection.
Right.
So then I show that generically the dual action has the Rocklin property, and the intersection of these things.
Got you. Okay.
What you want, yeah.
And is there some sort of general kind of connection between the Rocklin property and KMS states, or like outside of this kind of very specific example?
So in general, if you have the Rocklin property, you don't have KMS state.
Okay.
So this is a question actually I was thinking about. I don't know, like probably you can. I mean, in general, you can surely build examples where you don't have the Rocklin property and you don't have KMS states either. But I think like you are in classifiable setting, I'm not aware of any example where you don't have KMS states and you don't have the Rocklin property.
Okay.
But yeah, I can tell you after like a recipe for how to get this Rocklin property here. So it's like a duality. And essentially like alpha will have the Rocklin property if and only if the dual action will have some other property.
Okay, gotcha.
Right. So
gotcha. Right. Okay. Thanks. Anything else? Okay. Doesn't seem to be the case, so let's thank Robert again. Next week, is it Miriam next week? It's Miriam who will tell us about something. All right. So